Hi, everyone. Welcome to our webinar, 4 Requirements to Efficiently Deliver Real-Time Data at Scale. I'm Erica Fowler, Senior Product Marketing Manager for Molecula. I've got about 13 years experience in analytics and strategy across several different industries. I also have a PhD in epidemiology, which is where I found my love of analytics and most importantly, taking analytics and applying them to real world situations. I'm here today with my colleague, Dennis. Would you like to introduce yourself?
Hi, everybody. I'm Dennis Cody. I'm a product manager here at Molecula. A little bit about my background. I've spent like the last 10 years helping large enterprises in the public sector architect large-scale data solutions. So excited to speak about this topic today.
Me too. So before we get started, we'd like to introduce you to our company, Molecula. Molecula is a technology company that closes the gap between data and decision, enabling organizations to unlock the power of real-time analytics and AI. It's the creator of Featurebase, the ultra-low latency database at any scale. And we'll talk more about Featurebase today in depth as we dig into the 4 requirements to efficiently deliver real-time data at scale. Let's take a quick look at the agenda. First, we're going to set the stage for real time and what it takes and why it's so hard to deliver at scale. And next, we'll talk about how to actually deliver on those 4 requirements and how Featurebase enables all 4 of them efficiently without compromises. And finally, we'll wrap up with a Q&A and discussion. So if you have any questions, please drop those in the question queue. We'll get to as many of them as we can today, and we'll make sure to follow up after the webinar if we don't get to your question. So companies attempted to capitalize on big data and ran into high costs, rigidity, and extreme complexity with managing their on-prem stacks. So the modern data stack arose about 10 years ago as an answer to those problems that they were having with on-prem databases. So they shifted workloads to these cloud-native solutions that were designed to make the lives of engineers and other technical resources a lot easier. You have a lot of plug-and-play solutions for pretty much every part of the data and analytics lifecycle. And another major benefit of those is that they're actually built for the end user in mind. So they're a lot easier for those people to use, and they're more tailored to the specific use case that they're needed for. So the shift to the cloud, it intended to and did create greater simplicity and scalability while reducing costs. But this so-called modern data stack isn't really all that modern anymore, and it's definitely primed for innovation. So organizations are now struggling with the complexity that's currently involved in building these large-scale real-time data applications. In a typical modern big data architecture for just a single use case might involve anywhere from 5 to like over 20 different solutions or tools that are tied together to deliver that use case. And the process isn't repeatable, and it's still batch oriented. So, you know, those layers of this typical data stack built for a batch oriented world aren't really meeting the needs of real time now. So all of these different tools for ingestion, transformation, cloud data warehouses, all of these different specialized BI tools, they were all designed to deal with weekly, monthly reporting and taking action on that, digging into data ad hoc. But in today's world, real time is becoming more of an expectation. And it's really been ushered in with event streaming, things like Kafka, and brought in one step closer to fruition by these tools. But streaming data requires new technology to really take advantage of its capabilities. So let's look at a few use cases for real-time analytics. So we have 3 that we talk about, 3 like kind of pillars that we talk about here at Molecula a lot. We have improving customer experience and insights, detecting anomalies, and optimizing business processes. But there's also some other areas that are really starting to utilize real-time analytics that haven't been able to before. So we know like retail advertising and fraud detection, they've used this for a long time, but other industries like healthcare are starting to catch up. So traditionally, healthcare analytics, they've been limited to analysis of administrative claims data that are anything but real time. So you typically have a 90-day run-out period where a claim, it's going back and forth between the payers and providers, determining whether or not it's going to be settled and how fully it's going to be settled and who's going to pay for what. So you're never really working with real-time data, or you haven't been in the past. But now you have a broader adoption of the streaming data, including Internet of Things devices and a wider adoption of more standardized electronic health record systems. I know electronic health records have for a long time held a lot of promise for unifying analytics across healthcare, but in reality, each implementation of an EHR is pretty customized, so the data doesn't necessarily talk easily. But those are becoming even more standardized, and you're seeing companies be able to take advantage of different types of data. They're not limited to this administrative claims, traditional fee-for-service world, and there are other reimbursement models that are coming about, like value-based healthcare, bundled payments, et cetera, that are actually haven't been able to implement those in the past, but now that you have all these other new data sources, it's actually happening. And then one more example in healthcare that seems pretty extreme or rare, but it's becoming much more common, is like remote surgeries or robotic surgeries. So that's a situation where you absolutely need the lowest latency, you need stability. You know, seconds in those cases could mean a potential loss of life. Dennis, any other trends you're seeing?
Oh, I got a bunch of them. Honestly, real-time stuff has been a passion of mine. So whenever I got to work on a project in the past to do real-time data, I've always been really kind of giddy and excited. So some areas that are probably more typical, but are inherently real-time. I've done work with folks in cybersecurity, doing network intrusion and trying to detect anomalous traffic. If all of a sudden you start seeing a gigabit leave your network to country on the other side of the globe, you're probably going to be a little suspicious. I've done work with financial companies doing credit card transaction fraud, and I got to learn a lot about essentially why they keep declining me every time I travel. So I'm glad they keep me safe, and at the same time, it's better to know how to give them a notice ahead of time. And also in the finance space, just helping companies with low latency requirements of financial trading. There's areas like arbitrage, where time is of the essence to try to capture inefficiencies in the market and trade on them. And everybody's doing it. Whoever's basically fastest usually wins. So those are a few areas that I've personally been involved in that has been pretty cool.
Awesome. So, seems like a lot of people are trying to do this and a lot of people want to do this. So why is it so difficult? So why are even the most modern of data stacks still struggling to deliver real time? There are 4 requirements for delivering real-time analytics, and we've broken them down as low latency. So does your database return complex analytics queries in milliseconds? Freshness, is your data available for computation immediately after it's ingested? Throughput, can your system continuously ingest all the necessary data fast enough for real time? And concurrency, can you scale up and deliver thousands of simultaneous queries in milliseconds? So how do these 4 requirements translate to your stack?
All right, so why does your real-time architecture break? Erica listed out 4 requirements, and I'll walk through where typical issues arise that you may have in your own stack. It all starts with just getting data in. There's both hardware and software limitations. There's bandwidth and input output operation per second limitations on disks. But there's also just the overhead of trying to manage ingestion of millions of records a second. If I take any number, times it by 1 million, it starts to add up pretty fast. So right away, it becomes a challenge to get enough data in fast enough. Well, let's say you do that. Now we have the challenge of what we call freshness. getting it in and just stationary in the database is great and all, but if I can't run queries on it, does it even really exist? So in order to try to help with freshness, there needs to be a step of pre-aggregation to basically build out my use case tables and do so as fast as possible and as frequently as possible to keep that data up to date. Those are very expensive queries. And typically what I've seen is they'll be done maybe overnight, maybe on an hourly basis for real-time systems. So the most real time you can get at that point is an hour. Doesn't sound very real time. Then there's just, waiting for my my query to be finished. I'm sure people who in data science or data engineering, they run a query and all of a sudden it'll say 5% complete. They walk away, they grab a cup of coffee, they come back and they'll say 5% complete, and they kind of bang their head on a desk. So I actually have some stats here that I think are very interesting. What do we mean when we say real time? So two things. One, I found was interesting is people are really bad at gauging time if they don't have a clock in front of them. We perceive time, in the moment, 15% slower than reality. And we actually remember how long things take as being 35% slower. So, it just right off the bat, even though the clock says, it took a minute, it really feels like a minute and change. And now it kind of makes sense why the last day of school before summer always felt like an eternity. So that right there, it feels slow. Now, what does real time mean? There's sort of three numbers of real time used typically for like website loading. 100 milliseconds gives people the feeling they're in control. It feels instantaneous. That's the number to really try to hit. Now that's tough, but that's the goal. 1 second, users notice a slight delay, but they still feel in control. They know there's a little bit of lag, but it's okay. 10 seconds, they're gone. There's no more attention span. People just are gone. So the number to hit for is that 100 milliseconds. That's what real time means. And then finally, let's say we have those three. Now we have to prepare for the future. Real time is only real time if the user can actually run a query. Now that's a challenge because as more and more users are using the system at the same time, what resources you have to serve those queries keeps getting divided. So as you add more users, the amount of resources you can use per query diminishes. Now, that's a problem because when you diminish them, queries run slower. That's sort of the trade-off that I'll get into later. In the future, we got to prepare our data systems to be able to serve time-sensitive operations, which are typically going to be like a scalable application themselves. Think Kubernetes, all these sort of technologies. Now, if we have poor concurrency, the database now becomes the bottleneck of your entire data infrastructure. So that right there is a huge problem. Want to go to the next slide? So how do we fix it? The big one that we can get into next slide is one of the items is you pay a lot of money for it. You scale out and you kick the can of the underlying problems down the road. But we got some other workarounds as well. So some other common trade-offs, one I mentioned earlier was pre-aggregation. Rather than trying to do joins and build a table dynamically at query time, which is very painful, the common strategy is to simply build your tables ahead of time and just kind of scan through them. That will make your queries fast, but it's rigid, it's inflexible, and you still have to pay the cost up front. And you'll never hit that real time because those long running queries are typically only going to be run between an hour and a day. For ingesting, you can batch your records together. So a lot of times, whether it's network or disks or whatnot, when you batch things together, they run more efficiently. The problem there is, once again, you're your floor of latency or your floor of freshness is only as low as the time between batches. And that's not even to compound the issues everywhere else in your data stack. With concurrency, I can do prioritization. Certain queries are going to be more important than others, or I can simply, peg how much resources I will guarantee to a query. That's going to make them run longer, but I can at least serve more. Either way, that's a nasty trade-off that isn't fun to try to explain. And like I said, just, spend more money, horizontally scale out. Every database solution says they can do it. That works great for maybe 10 to 100 nodes, just from personal experience. Beyond that, the overhead, both financially as well as technically and like organizationally, explode. You need to hire far more people to maintain this, essentially now a data center. You need to deal with exorbitant overhead, just of architectural complexity. It's not fun, and really at some point around 1,000, you're going to go, I made a mistake and I don't know how to get out of this.
Definitely. I think the one I've had the most experience with as an analyst is the first one that you mentioned is pre-aggregation. Also you may hear it called denormalization. So if you've worked with roll-up tables or data marts, then you've definitely worked with pre-aggregated data. And this is typically done to, as Dennis mentioned, to speed up latency or the query speed for the end user, and results in the, stale data. So it's interesting. A lot of people just think that pre-aggregation is something that you have to do because it's such a common workaround. So it's really exciting to know that there are emerging technologies that are helping us get past that common workaround. All right, so how to actually deliver real-time results. So this is an example, a case study of a customer of Molecula that we have helped do some things they've never been able to do before. So our customer is a provider of technology-driven video advertising solutions, and they are using Featurebase to power real-time insights based on different user actions that are happening in real time. So this allows for automatic and manual calibrations of media buying, and it results in just much more efficient campaigns. So they're able to spend their money where it really matters on these campaigns. They were trying to do this with traditional column-oriented analytical databases, and they just weren't able to meet their needs. So with Featurebase, they're able to serve ultra-low latency queries. And we've improved their ingest rates to 1 million events per second, which is mind-blowing. Once you get to about like 200,000 per second, that's considered a lot. So thinking 1 million is just mind-boggling to me. And we're able to do that without sacrificing the latency part of the queries. They're able to update more than 30 billion events per day across 5 billion records. So they have all of these, billions of events coming in, and they're updating them, which is another thing that they were having issues with using Columnar. They've also been able to handle 200 concurrent queries while maintaining the 1 million records per second ingest and their low latency querying. So really, really exciting. And Dennis has mentioned money a couple times. One of the most exciting parts of this is they were estimating that it would cost them 100 clusters to do this on another technology, and with Featurebase they're able to do this with 9 servers. So very, very exciting, and one of the best examples we have of meeting all 4 of those requirements very efficiently. So how do we do this? Featurebase is the foundation for AI-ready data. It's a feature-oriented database platform that is purpose-built to unlock this power for real-time analytics and for AI. So we'll go into a little bit more detail, but we can do millisecond queries. We can reduce the compute costs necessary to run all of these analytics because we're so much more efficient. We can do this on your freshest data. There's no need for pre-aggregation, so you can, cut out that workaround that causes stale data. And we have our data format is highly optimized, so you can get 10 times or more like data compression from the source data to what is stored in Featurebase. We structure data in a way that requires minimum I/O or input-output for analytical queries. So we break the data down into an individual value that is still addressable without any loss of your data, which is really cool. You don't have to federate the queries or go back to the source data. It's all there in Featurebase. We're also very, very good at processing data in parallel. So each shard of data that's there can be processed in parallel. And then our format also plays extremely well with the CPU, particularly how CPUs try to predict what data to load. And I think, Dennis, you're going to go into some more detail about the CPU part of this in a little bit.
Sure.
All right.
Yeah. So data freshness. So we have a slightly enhanced data model compared to a lot of other relational or columnar data sources. And so one of the interesting things is that besides the high throughput we can get by pre-extracting features, which ultimately reduces how much data that we have to move around and transform and prepare for querying, the actual data model itself, we have very scalable tables. And so we typically think of a table as being billions of columns and trillions of rows. And what that allows for is we can co-locate sort of your objects with actions. So think like, an object being like a user and an action being maybe, things they've purchased. Rather than having different tables for them, we can actually co-locate them in the same table because we have so much room to lay out features and process with. Now that both simplifies the querying aspect of it, because now all of your use cases in one table, but it also allows us to avoid having to do any sort of joins. So, or, and like I said, any sort of pre-aggregations, because from the start, we're already putting it right where it needs to be.
I know as an analyst, I've given a lot of data engineers heartburn trying to do this in SQL and joining all the facts back to the dimensions and creating this one beautiful table that I could use for analytics, but it would be like, Erica, you cannot do that. So
the old create table as select.
Yes. Sorry for everyone that I've kept up late at night and crashed your database. But as I mentioned before, as an analyst, the pre-aggregation workaround is something that, until I was introduced to Molecula and Featurebase, I thought it was just something you had to do. So very exciting. So high throughput, we can scale out horizontally and add more servers and more cores pretty much indefinitely to scale up the ingest. We excel at updates because we're storing so much less data fundamentally, so there's less to read and write. And one thing that we do that's a bit unique is during ingestion, we do key translations on the client side. So you not only have the option to scale out your actual database servers, you can offload a lot of the computation to the ingest servers, which can be ephemeral and exist only while there is ingest load coming in. So you can spin up new servers for ingest based on the volume that's coming in without impacting your query latency on the other side. And those things are often tied together, but with Featurebase, they are decoupled, and it's a really cool superpower of Featurebase. All right, and then concurrency.
Yeah, so concurrency, got some notes here. So one of the things that we do is what we call MVCC transactions. It's pretty old school, but it works really well, and that's why we use it too. And what that allows us is we can always guarantee the ability to read and make sure that even when writing, whatever the the previous data that is still the committed data can still be read. And so that allows us to avoid blocking queries simply because we're waiting for the ability to read from a database. We are also very CPU and memory optimized. And so that allows us to be very lightweight, which, because once again, we're using less resources per query, we can inherently service more clients. And then finally, this one sounds like, well, anybody can scale. What's interesting is that a lot of other database systems, there's sort of a minimum amount of overhead for every time you add another node or you create another instance. Because we're so lightweight, we minimize that overhead, and we'll use every bit of hardware, whether we scale up or scale out, as we can. And so by just optimizing our usage of the resources, that allows us to eke out an order of magnitude or two more clients at a time.
I really appreciate this one too, as an, with an analytics background or data science. There's a lot of times your queries get queued, and this is what's happening. The database that you're working with can't support concurrency. So you're, sometimes depending on even like what level of analyst you are within the organization, your query goes into this queue, and there have been times when my team, we've kicked off queries at night to come in the next morning only to find someone like Dennis has shut them down because they're taking up too much.
Hey, I need my stuff to go through. That's way more important.
Right. Okay. So yeah, this is really exciting. So talking machine to machine and like thousands of machines, querying at the same time. But even for for an analytics organization that has multiple users querying a database, this can also be really, really beneficial. All right.
Yeah. So I've snuck in the word budget a few times in this presentation so far. And that's just the way I kind of think about this problem, is with any database system, you only have so many resources, CPUs, memory, network bandwidth, and you can't, without spending an exorbitant amount of money, increase that. And so you got to optimize with what you have. Now that means trade-offs, just like any sort of budget. Now we've talked about the LFTC, and I like to think about when and how do I pay for these things. So with latency and freshness, you have to pay them upfront. And what I mean by that is, for, let's say, latency, you have two choices. You can have very expensive and fast queries, or you can have very cheap and slow queries. And by expensive and cheap, I mean, how much resources are you using? And then same with freshness. Do you break down your pre-aggregation into multiple steps, or do you do it all at once? But either way, you have to do it all before you can ever start querying on that new table. So these are costs that you have to pay just upfront. You can't really sprinkle it out over time. Whereas concurrency and throughput, which is really how much in parallel goes in versus out, it's really a matter of dividing up my resources. As I have more and more inputs, or I have more and more queries, my resources are divided, but they're also divided between ingest and querying. And that's because ultimately, with your resources, especially a CPU, they can only do one thing per core at any given time. And so you ultimately have a choice. Do I dedicate it to ingesting and storing data, or to analyzing for queries? So something, once again, I like to talk about is, so we have cost, we have budget, what's the unit? I've thought about this, and I've kind of dabbled around with my experiences, and ultimately the cost is bytes. How much memory do you need to use? Well, we measure that in bytes. How much traffic? How many bytes are you sending across the wire? How many bytes are stored on disk? Even CPU usage, which is either usually like a percentage or a time number, that's actually really depending on the underlying, like without getting too much into it, how many clock cycles do I have to do to process all this data? Because CPUs don't really care about time. They just execute instructions as they're given. And so even CPU usage, I can say, is a form of bytes, because, you know, for 64-bit processors, the question is really, how many 64 bits of data do I need to process to complete my algorithm? So, you know, these four areas, which are always sort of the main culprits of bottlenecking, they're all based on the size of the data being stored, being processed, and being transmitted. So with sort of the my understanding of how budgeting works, I'd like to kind of apply it here to a row, typical relational database, a columnar database, and then what we do in Featurebase. So in a row-oriented database, so they're great on filtering by primary key, and so you can kind of skip around the different rows. But for analytical operations, I care about the data set as a whole. And what that means is I ultimately have to read all of the data in the table, and then I throw away the stuff that I actually don't care about, because how databases are going to read this is like a book. They're going to go top down, left to right. In this particular case, I went through the effort of counting how many bytes besides the primary keys there, and I have 92 bytes of data. I mean, small table, but I'm going to show you why that's impressive when we get to the feature-based stuff. All right, so with columnar databases, the big innovation there is, instead of having to read it like a book, top down, line by line, I can focus on only the columns that actually matter. And so in this case, you can kind of think of the table being, transposed. And if I'm only interested in, what's my distribution of manufacturers, I don't have to read type, I don't have to read year. I can go right to manufacturer, read just that bit of data, and call it a day. So that's really the big innovation of columnar. The challenging bit is, this is obviously a small table, but let's say I want to know how many routers and switches were made by Juniper or HP in 2017. Well, I just used all the fields, so I still have to read all the data. So now we get to how we store data in Featurebase. We break out the values, and we store each value only once. And then instead of having to duplicate the actual value, we just store relationships of these features to the records themselves. And we can store it as a single bit, a 0 or a 1. Now, what's going to become very powerful here in a second is, a bit is 1/8 the size of a byte, and we're also not having to duplicate any of the records. So calculations are correct. We only would need to read, in this particular case, to show all routers or switches manufactured by Juniper in 2017 with 24 bits or 3 bytes. That is a 97% decrease in how much data is being read.
That's awesome. And these were these slides that I saw the first time that I was introduced to Molecula Featurebase. This is what was presented to me, and my mouth just dropped open, and I was like, "Are you serious? This is so amazing!" So really exciting stuff, and we're excited at Molecula to be ushering in the rise of real time and actually being able to act on it. So with that, I think it's time to.
Hold on, let's go back. Yeah, go back for a second. While we're here, I also want to point out why we're CPU efficient. It's going to get a little bit into the weeds here, but by operating on binary data, besides just inherently reducing it by 97%, we're playing to the strengths of both caches in your CPU and the CPU and how it wants to do operations itself. And so because of that, we can take full advantage of the fact that a typical processor nowadays is going to do about 7 billion operations a second. We can do native instructions on a CPU. And what that allows us to do is literally do 7 billion operations of, feature-based operations a second. And so whether it's intersections and unions of data, which is going to be your ands and ors, or if it's counts, those are all instructions used by CPUs, and we can take complete advantage of that.
Awesome. Thank you, Dennis. So now we're going to go to the question queue and see what we have there before we call it a day here. So let's see, we have 2 questions. So Dennis, you mentioned trade-offs. What are your trade-offs?
There's no trade-offs. It's perfect. Oh, I'm supposed to give a real answer. Okay. Yeah. So right. There's no such thing as a free lunch, and ultimately, we do have a trade-off. Now, where our trade-off resides is actually right here on this slide. Our format is tailored for machines, and it's tailored for CPUs. Now, as a human being, if I see a bunch of ones and zeros, I'm going to be very confused of what I'm seeing. So in order to what we call rehydrate the table and make it more so like you would see in other database systems, we have to go back through and replace the ones and zeros with those keys again on the left-hand side. That's a pretty intensive operation for us. But in the world where we're just really trying to get analytical answers, it's actually not necessary. And so when we're building out capabilities for applications that are trying to do real-time analytics and trying to project and do regression analysis or what have you, they don't care what the label is. They care just that it's the same data, the same series or whatnot. So that's the trade-off. We push aside where we think it doesn't matter in the future, and we lean into what we think is really going to power AI/ML use cases in the near future.
Yeah, I think of kind of what you mentioned, it's the machine ready format, and all of this is at really large scale. So that's another thing. Like even if a human was looking through the data and after it was rehydrated, we're talking about so much data here that like it's not really feasible for a human to actually look at it anyway. So that's why this is machine ready, machine to machine interactions, and is really built for this rise of real time and delivering all of these requirements at scale and very efficiently. So yeah, thank you. That was a great explanation. All right, we have one more question in the queue here. If you have other questions, please, feel free to reach out and, we can chat via email, get you in touch with one of our sales reps, or, go to the website and request a demo. That's also an option. So this one is, Featurebase can handle trillions of records, but if my data is sparse, does that impact query latency?
Yeah, that's definitely a question that I had, especially coming into Molecula, because the ideas of working with ones and zeros, it's been around for other database systems in a very naive format, because we're still storing a bit for every record. So in my head, right, I'd kind of be like, well, is that really just reducing the size by 1/8? And the answer is no, and that's because our format doesn't just use a naive set of binary ones and zeros. On top of doing that step, we actually also apply a bunch of encoding and compression algorithms that remove most, if not all, of that that sparsity. And so it's actually pretty phenomenal, the the data compressions that we can get, you know, I think the number you said earlier, Erica, is 10x, which is 90%. That's pretty on par for customers. Between 90 to 99% reduction in the data size because of removing the sparsity and leaning into features. So TLDR, sparsity is actually something that is one of our strengths.
I think another thing with this, the data size and data compression and, you know, real-time analytics, something worth mentioning too is to do these real-time analytics, you know, you have the streaming data, but on its own, it's not enough. You also need to have historical data with that. And because of our compression, we're just able to handle so much more data than most databases are able to handle, and do it so efficiently that we're able to, our customers are able to do things that they've never been able to do before. So really exciting, having enough data to really do granular forecasts and granular predictions, because maybe in the past you were limited to storing only a certain amount of historical data or whatever based on your system limitations. We're really ushering into a completely like new territory with some of the things that we're seeing our customers do. So yeah, definitely able to handle these large data sets. The sparsity's not an issue. We still get the query latency. So yeah. Well, those are all the questions that we have today. Thank you for joining our webinar today, and I hope that you enjoyed hearing about real-time analytics, the requirements, and also how Featurebase can help deliver on those without compromises. Yeah, and if you want to learn more, please go to our website and request a demo.